Okay. All right. So make sure this is on. Okay. So today we will start chapter 6, which is entitled Understanding Organic Reactions. We certainly will not have a complete understanding of organic reactions once we finish this chapter. But the goal is that we will understand some of the fundamental principles that will allow us to understand the specific reactions that we will start learning in chapter 7. So today we'll talk about types of reactions. We'll talk about how bonds are broken and formed. And then we will discuss some of the principles of thermodynamics and how they apply to organic reactions. So first of all, we have some different ways of writing reactions shown here on the screen. Unfortunately, we don't have a uniform method of writing organic reactions. So we've shown you a couple of different ways that this can be done. You will always see the starting materials of the reactants on the left side of the arrow. Okay, we see that in both cases here. You'll see the organic products drawn on the right side of the arrow. And then many times we have inorganic reagents that are reacting with our starting materials. And sometimes those reagents are shown above the arrow. So both of these reactions have bromine. This is the same reaction shown two different ways. But you see that bromine can appear above the arrow as it does here and here. Or sometimes it's shown on the left side. So either way is the same. Question? A very slight difference. The words are often used interchangeably, but when you say reagent, usually that's something that you buy to react with your organic starting material. So it's oftentimes an inorganic species, such as an acid or a base or a halogen in this case, that's reacting with an organic compound. So reagent is a little more specific than reactant, right? Anything that's participating in a reaction would be a reactant. But a reagent in this case would be bromine, and this would be a starting material, but both of those are reactants. And then you see that the solvent is sometimes included, sometimes it's not. There's probably a solvent used in this reaction, but it's not shown under the arrow. So sometimes we leave off details. It all depends on what we're focusing on. Even if we might leave the solvent off of our equation, it's still important. I've written for you here some of the purposes of a solvent. So the first thing a solvent does is it gets the reactants into a single phase. In order for a reaction to occur, the reactants must collide. And it's much easier for them to collide if they're in the same phase. So if both of the reactants dissolve in the solvent, then they are in the same phase and much more likely to collide with each other. In addition to that, solvent molecules can interact with molecules in the reaction, such as intermediates. We'll talk a little more about reactive intermediates later today, and we'll learn about transition states on Monday. But intermediates and transition states are species that are produced on the pathway between reactants and products. And sometimes the solvent can stabilize those through non-covalent interactions, such as van der Waals forces or hydrogen bonds. And if it can stabilize those intermediates and transition states, it can lower the energy barrier for the reaction and cause it to occur faster. And then other times, solvents can serve as a heat reservoir. If we have an exothermic reaction, heat is generated in the process, heat is given off. If too much heat is given off too fast, then sometimes you can have problems. Sometimes you can have decomposition of your products that form if you have too much heat. Sometimes you can have explosions. So those are undesired outcomes. But because you have a lot of solvent molecules, many times those solvent molecules can absorb that heat and prevent that heat from doing damage to the products of your reaction. So Three important roles for solvents. Even when solvent is not written down here, then solvent is still an important part of organic reactions. And then some reactions are promoted by heat or light. Sometimes the energy that is required for a reaction to occur is delivered to the reaction, either in the form of light or heat. And that is shown in these two different ways, using Greek letters. So this is H nu, it's not HV. H nu tells us that light is being added to a reaction. And then this is not just a triangle, this is the Greek capital letter delta. And delta is the symbol we use to indicate that heat is being added to a reaction. So we'll see these, one of these symbols when heat or light is involved in a reaction. Okay. Any questions about how we write organic reactions? One more thing I'll tell you is that we're not trying to balance equations. So in general chemistry, you probably focused a lot, and in high school chemistry especially, a lot on balancing equations. We're not so concerned about balancing equations in organic chemistry. We're more interested in what is our organic starting material, what is our organic product of the reaction. You'll notice this particular reaction, we're replacing a hydrogen atom on cyclohexane with a bromine, and we're generating HBr in the process, but we don't see HBr listed anywhere in this reaction. That's because HBr is an inorganic species. We don't care about inorganic species in this class. Not really, that was a little bit of a joke. But it is not the product we're looking for in the reaction, and it is very easy to separate from the organic product. Okay? HBr is going to be water soluble. This product here, bromocyclohexane, is going to be insoluble in water. So using the physical properties, it's very, very easy to separate that HBr byproduct from the bromocyclohexane. So we wouldn't even pay any heed to it or think about it at all because it's so easy to get rid of. So we're only focused on the organic starting material, the organic product. So many times inorganic byproducts are left off in these reaction equations. All right, so we need to understand different types of organic reactions. The book provides a very helpful classification of organic reactions into 5 different types. The vast majority of reactions will fit very neatly into one of these 5 categories. And the first one is one that you've already learned, acid-base reactions. We're not done with acid-base reactions just because we're done with the acid-base chapter. We will see acid-base reactions throughout the class, okay, all the way through 352. And then another category of reactions you're familiar with from general chemistry are the oxidation-reduction reactions. The book mentioned them briefly in chapter 4. We skipped over that in class. We'll revisit that when we get to chapter 12, which focuses on oxidations and reductions more extensively. But this is a class of reactions that you're familiar with from general chemistry, and there are plenty of organic reactions that are considered either oxidations or reductions. So the next category is one that might be less familiar to you. And that is the substitution reaction. Okay. So in a substitution reaction, an atom or a group of atoms is replaced by another atom or a group of atoms. So in general form, we could draw a substitution in this fashion. So Z is going to be our atom or group of atoms that's getting replaced. Sometimes it's a heteroatom, such as a bromine or a chlorine. Other times it can be a hydrogen. But we react that with another substance. We'll just call it Y in this particular case. And what we'll find is that Y is replacing Z. Do we have a substitution up on the screen here? Which one is the substitution? Okay, the one on the right. And somebody answered the next question I was going to ask. What is being substituted? The H, the hydrogen, one of the hydrogens on cyclohexane, is being substituted or replaced. And what is it being replaced by? Bromine. Okay, very good. This is a radical substitution reaction. We'll learn more about that in chapter 15 at the very end of the semester. So in a substitution, I'll back up a minute. In any reaction, it's important to understand which bonds are being broken and which bonds are being formed. So in this case, in a substitution, what kind of a bond is being broken? A sigma bond, okay? And what kind of bond is being formed? Sigma. So we're replacing one sigma bond with another. Sometimes that doesn't tell the whole story. In this reaction, we're breaking two sigma bonds and forming two sigma bonds because of the bromine-bromine bond that breaks and the HBr bond that's not shown that's being formed. But at a minimum, we're going to break one sigma bond and replace it with another one in a substitution reaction. Okay. So our fourth category is elimination reactions. Okay. So in an elimination, two groups that are present on the starting material are lost and they're replaced by a pi bond. Okay. So we'll draw a generic version of this. Okay. So here's our starting material. We have two different groups, X and Y, on adjacent carbons. And we lose those, and we replace that with a pi bond. So what kind of bonds are being broken in an elimination? Sigma bonds. What kind of bond is being formed? Pi bond. Many times there's another sigma bond that's formed as these groups are lost, but if you're looking at what's happening to the starting material in the product, we're breaking two sigma bonds and forming a pi bond. Okay? So we don't have an elimination on the board, so I'll go ahead and draw one for you. So we could take this molecule, bromoethane. We could react it with this species, sodium tert butoxide. This is a base. We'll learn more about eliminations in chapter 8. But this base could cause this elimination to occur, generating ethylene as a product and a couple of byproducts as well that we'll worry about later. Question, Claire? Yes, that's a very good point. So you could refer to this as an acid-base reaction as well as an elimination. And then we're going to have oxidation reactions that are going to fit, oxidations or reductions that are going to fit in some of our other categories as well. So indeed, some reactions will fit into more than one category. Good question. All right. And then we have our fifth category, which is addition reactions. And in an addition reaction, two groups are going to be added to the pi bond of the starting material. So addition reactions are the opposite of elimination reactions. In elimination reactions, we're losing groups and forming a pi bond. In an addition reaction, we're gaining groups and we're losing the pi bond. Okay? So here's our starting material with our pi bond. Here's our reagent XY. And then in our product, we're going to have X on one carbon, Y typically on the adjacent carbon. What bonds are broken in an addition reaction? Pi bond. And then in many cases, we'll see a sigma bond in the reagent that's broken. And then what bonds are formed? 2 sigma bonds. Okay, very good. So you see it's just the opposite of the elimination. Do we have an addition reaction on the screen? Yes, the one on the left is an addition. It's called a bromination. That's a specific type of addition reaction. So we are adding bromine, a bromine atom to each of the carbons of the alkene in this particular process. Okay? Any questions about our 5 types of reactions? There will be a handful of reactions that don't fit very well into these categories, although the ones that we'll learn in class, the vast majority will. And then as Claire mentioned, there will be cases where there will be some reactions that would fit into multiple categories. Okay? All right, so let's talk about bond breaking and bond making. We've analyzed our different categories of reactions in terms of bonds that are formed and bonds that are broken. And this is a helpful way of understanding how organic reactions proceed. All organic reactions will involve bonds being broken and new bonds being formed. So we have a term, reaction mechanism. Okay. So a reaction mechanism is a detailed description. Detailed description of how bonds are broken and formed as starting materials. This is an abbreviation I like to use for starting materials are converted into products. Okay? That's an abbreviation I like to use for products. So, describing the process of how the starting materials are converted into products, which bonds are broken, how are they broken, which new bonds are formed, how are they formed, that is a reaction mechanism. And we'll start learning reaction mechanisms in our next chapter. So, a reaction mechanism must be consistent with all of the known data regarding the reaction in question. Okay, we can collect data by running experiments, and those data can give us ideas about how the reaction occurs. Sometimes new data are generated that are not consistent with the reaction mechanism, in which case the reaction mechanism must be modified. If a reaction mechanism is not consistent with all the available data, then it's not accurate. Okay? So many times a reaction mechanism is proposed, and then additional experiments are conducted, and that reaction mechanism is modified as a result. Okay? But in this class, the reactions we'll be studying are generally well-known reactions, and the reaction mechanisms are well accepted. They've stood the test of time. Okay? There are 2 types of reaction mechanisms. A concerted reaction mechanism. In a concerted reaction mechanism, we have starting material or materials A, that get converted directly into the products B in a single step. Okay? So when we say a reaction mechanism proceeds in a single step, what we mean is that there are no intermediates that are formed. Okay? That means that all of the bond breaking and bond making events are occurring simultaneously. Okay? We're not generating an intermediate species that then gets converted into the product. So concerted reaction has a single step. All the bond breaking and bond making events are occurring simultaneously. And then you might imagine the other type of mechanism would be the stepwise reaction. Okay? So in a stepwise reaction, we are going to have our starting material or materials. We'll convert that into B, but then B is going to undergo further transformation, and then C is the final product that we're isolating from the reaction. And so B would be referred to as an intermediate, or sometimes we call it a reactive intermediate to remind us that B is typically a transient species. It's usually a high energy species. It's usually not something that you could isolate from a reaction, put in a bottle, and store on a shelf. It's usually something that once it forms, it is then further transformed into the product, and so it usually only exists in your flask, in your reaction flask, for a short period of time. Okay? Any questions? All right, so let's talk a little bit about how bonds are broken. There are two ways we can break bonds. One is referred to as homolysis or homolytic cleavage. Okay, so the homo prefix, meaning the same, tells us that the electrons in a homolysis are divided equally between the two atoms that were involved in the bond. Okay? So, in a homolysis, one electron in the bond goes to one atom, the other electron goes to the other atom, and so we form intermediates with unpaired electrons. And those intermediates with unpaired electrons are known as radicals. We'll talk a little bit more about radicals in a moment, and we'll talk about them in more detail in the last chapter of the semester, chapter 15. So our second type of bond-breaking method is called heterolysis or heterolytic cleavage. So you can probably guess that in a heterolytic cleavage, the electrons in the bond are going to be divided unequally. Hetero meaning different. So both electrons will go to one atom and the other atom won't get any. So typically when we have a heterolysis, the more electronegative atom that was involved in the bond is going to get both electrons, and then the less electronegative atom is going to get no electrons from that bond breaking process. So on the screen here, you can see how we can draw homolysis and heterolysis. We have, we'll look at the heterolysis first. So we've already learned that a curved arrow shows the movement of a pair of electrons. And so in this case, Z is more electronegative than carbon. And so as that bond is cleaved heterolytically, both electrons are going to Z. And that gives us an anion. And then it gives us an intermediate with a positive charge on carbon. And we refer to that as a carbocation. And we'll encounter carbocations in chapter 7 and in several of the chapters after that. They're very common reactive intermediates. Okay? And then this carbocation, because it's an intermediate, it's going to react further with some other reagent to give the final product of the reaction. Now, rarely, but not impossibly, Z could be less electronegative than carbon. If Z is a metal, for example, if you have a carbon-metal bond, then a heterolysis of that bond would cause the electrons both to go to the carbon, generating a carbon with a negative charge, a carbanion. That's also going to be a reactive intermediate, a high-energy species, similar to the carbocation, that would then react with something else to go on and give the product. Okay? Homolysis is shown a little bit differently. Question? Good, good. Always good to answer your own questions. All right. So homolysis has to be drawn differently because our curved arrow is showing the movement of a pair of electrons. But when we perform a homolysis, we don't have a pair of electrons. We have single electrons that are moving in different directions. So we use a different type of arrow to indicate the movement of a single electron. And that is a half-headed arrow, which is also sometimes referred to as a barbed fish hook because it looks like a fish hook. And so here we see that one electron is going to Z, one electron is going to the carbon. And so we end up with intermediates that have unpaired electrons that are referred to as radicals. Okay? So these are our three types of reactive intermediates that we will encounter in organic chemistry: radicals, cations, and anions. Is our carbocation going to be an electrophile or a nucleophile? Okay, it's an electrophile. Yes, that's going to be a Lewis acid or an electrophile. Carbanion, electrophile or nucleophile? That one's a nucleophile. Okay. What about our radical? It's hard to tell with our radical. We can use the terms electrophile and nucleophile with radicals, but it's not as helpful as it is with cations and anions. So what we recognize with radicals is that because they do not have the octet, they are always very reactive and they're always seeking out another electron to be able to form the octet. Okay. All right. So the book tells us that there are two ways that we can form bonds. It says that two radicals can come together, and there we would use our barbed fish hooks to show that bond formation process. It also shows us that a cation and an anion can come together. There we'd use our regular curved arrows to show the bond forming process. This is not comprehensive. There are other ways of forming bonds that we will see in the class. But the one thing that these two methods and all of the methods that we are going to learn for bond formation have in common is that all of them release energy. Okay? So both our homolysis and heterolysis require energy. Breaking bonds always requires energy. And forming bonds always releases energy. Okay? So that's something we need to remember to understand the energetics of reactions. And then there's a very nice table in our book showing us the types of arrows that we will encounter in organic reactions. These arrows are part of the language of organic chemistry. If you're going to speak the language of organic chemistry, you have to understand how these arrows are used and apply the proper arrows in the proper situations. So this is a regular reaction arrow. This is an equilibrium arrow showing an equilibrium process. We'll talk about coupled reaction arrows on Monday. We encountered the double-headed arrow with resonance structures, and it's important to recognize the double-headed arrow is not the same as the equilibrium arrow. They're different. This is used for an equilibrium reaction. This is used when you're drawing resonance structures. Then we have our full-headed curved arrow showing the movement of a pair of electrons. We've used those curved arrows with resonance structures. We will also use them when we draw reaction mechanisms. And then we have our half-headed arrow, or our fish hook, that we use to show the movement of a single electron. We'll see those primarily in chapter 15 when we are studying radical reaction mechanisms. Okay? Any questions on our types of arrows that we encounter in organic chemistry? Okay, let's talk about a little more about how bonds are broken and how we measure the energy that is given off when bonds are broken. So there's a term, bond dissociation energy, okay? Often abbreviated as BDE. So bond dissociation energy, or BDE, is the amount of energy that it takes to cleave a bond in a homolytic fashion. Okay, these are our two barbed fish hooks showing that we're cleaving the bond between A and B in a homolytic fashion, and we are generating radicals as a result of that process. Okay, we know that bond breaking requires energy, so this amount of energy would be a delta H for this reaction. Would it be positive or negative? If energy is required, if it's endothermic, is delta H positive or negative? It's going to be positive, exactly. So our bond dissociation energies are always going to be positive values, and they're going to be measured either in kcals per mole, the units we typically prefer in this class, or they could be measured in kilojoules per mole. And this table shows both. Okay. So this is not a table that you want to memorize. So please don't memorize this table. It's not valuable in any way, shape, or form to memorize these numbers. What is valuable is to understand the trends that appear in this table. Okay. So by the end of the class, we should be able to understand all of the trends in terms of the bond dissociation energies increasing or decreasing as we compare two or more of those values in this table. So let's start with ones that we should know already. Let's take a look at the top four bonds. This category are X bonds. Those are bonds between carbons and halogens, halogen atoms. So we have different types of alkyl groups shown here. The first four are methyl groups. So we have bonds between a methyl group and a fluorine, chlorine, bromine, and iodine. Okay. Which of those bonds is the strongest? Carbon fluorine. Which of those bonds is the weakest? Carbon iodine. Who would like to raise their hand and explain why those bond dissociation energies go down as you're going down that column in the table? Yes, please, Grace. Okay, excellent. So you said that iodine is a bigger atom. Iodine, therefore, forms longer bonds. We learned in chapter 1, larger atoms form longer bonds. We learned that longer bonds are weaker bonds. The electrons in the longer bond are further away from the nuclei, and so they're not attracted as strongly. Therefore, it's a weaker bond, and therefore it requires less energy to cleave such a bond. Okay? So that's the reason for the trend. That's the explanation. And we see that trend manifest in these differences in energy, roughly 15 to 20 kcals per mole difference in energy in those carbon-halogen bonds as we go down the column, as we go down the column of the periodic table. Questions? Yes, please. So the principle that shorter bonds are stronger, longer bonds are weaker. That's a general principle. That doesn't just apply to the bonds to halogens. All right, so we can use the values in this table to give us a general idea of whether a given reaction is going to be thermodynamically favored or unfavored by looking at the amount of energy it will cost us to break the bonds that are broken in the reaction, and the amount of energy that would be released by forming the bonds that are being formed in a reaction. So let's look at an example. Okay, we have this compound, tert-butyl chloride. We could also call it 2-chloro-2-methylpropane. We're going to react it with water. This is going to be a substitution reaction. Okay. So we're going to replace the chlorine with an OH group. And then we're going to form HCl as a byproduct. Okay. So first, let's look at the bonds that are broken. Which bonds in the starting materials are broken in this reaction? Okay, we have a carbon-chlorine bond. And it's a carbon-chlorine bond to a tert-butyl group. Do we have such a bond in this table? Okay, what is the bond association energy in kcals per mole for that bond? 79. Okay, it's right here. Here's our tert-butyl group. Here's our chlorine. 79 kcals per mole. That's how much energy it's going to cost us to break that bond. Okay. What other bond in the starting materials is being broken? Okay, an OH bond in water. And how much energy does it cost us to break that bond? We can find it 119. That's a very strong bond. You might think, why on earth is that bond so strong? It's broken all the time in acid-base reactions. Well, remember that the way we define bond dissociation energy is homolytic cleavage, where we're breaking the bond homolytically, and in an acid-base reaction, it's a heterolytic process. Okay, so that bond can be broken. We have other acids up here that have fairly strong bonds in them, but those bonds can still be broken in a heterolytic fashion fairly easily. Okay, so we can add these numbers up. We add them up, we get 198 kcals per mole. That's how much energy it's going to cost us to break these two bonds that are broken in the reaction. All right, what bonds are being formed? We're getting a carbon-oxygen bond to a tert-butyl group. Okay. How strong is that bond? Can we find that? It's here somewhere. Okay, there it is, 96, right here. 96 kcals per mole. Okay. What other bond is formed? HCl. And what's the bond association energy for HCl? Okay, 103. Now these bonds are being formed, so energy would be being released, so we could put negative signs in front of those if we wanted to. So we add those up. We would get negative 199 kcals per mole. So in this case, the bonds that are formed, I'll put the squiggly line here indicating that that's the bond that's being formed. The bonds that are being formed are slightly stronger, just barely, but slightly stronger than the bonds that are being broken. So in this particular reaction, we would conclude that it should be thermodynamically favored. Not by a whole lot, but it should be thermodynamically favored. Okay. So this method of analyzing organic reactions is not foolproof. It is simplified. It has some limitations. It doesn't account for the reaction mechanism because these numbers come from homolytic cleavages, and the bonds may or may not be formed homolytically in the reaction. It doesn't account for a role that the solvent might play. We've ignored that. And it doesn't give us any information about the rate of the reaction. So there are two concepts that both relate to organic reactions, but they relate in different ways. We have thermodynamics, which is the study of the relative energies of the reactants and the products. That's determining whether or not a reaction will be favored at equilibrium, whether or not the products are more stable than the reactants. And then we have kinetics. Kinetics is the study of reaction rates, or how fast a reaction occurs. And these two characteristics are largely independent of each other. We can have reactions that are highly thermodynamically favored that may take months or years to reach equilibrium. On the other hand, we can have reactions that are unfavored, but they reach that unfavorable equilibrium within seconds. So this analysis doesn't tell us anything about how fast or how slow the reaction would occur. It just tells us that it should be slightly thermodynamically favored. And the reason for that is the bonds that are formed are stronger than the bonds that are being broken. It's important to recognize that this is the case in ATP hydrolysis, which I've mentioned previously, that you may have heard if you've taken biology classes. You may have heard that energy is stored in the bonds of ATP and energy is released when those bonds are broken. And I've already told you a couple times that that's not true, that it always requires energy to break bonds. And so the more accurate way to state it is that when ATP is hydrolyzed, the new bonds that are formed are stronger than the old bonds that are being broken. Now, that's the case here, and that's the case in ATP hydrolysis and any other reaction that is thermodynamically favored. Okay? So, a couple of thermodynamic parameters that we need to discuss. KEQ, or the equilibrium constant. What is our definition of KEQ? Just the general chemistry definition is fine. The concentration of the products divided by the concentration of the reactants. Okay? So if we have a favorable equilibrium, is our KEQ greater than 1 or less than 1? It is greater than 1 because the products are going to be in higher concentration than the reactants. Okay? Then we have an equation. We looked at this equation in chapter 4, and you're also familiar with it from general chemistry. Delta G naught equals negative RT ln K. This relates the Gibbs free energy of a reaction to the equilibrium constant. So does a favorable reaction have a positive or a negative delta G? Negative, exactly. Because the energy of the products is going to be lower than the energy of the reactants if the reaction is favorable. And it's always products minus reactants. And then you see here, because of this negative sign, if we have a K that's greater than 1, ln K is going to be a positive number, and that's going to make the delta G a negative number. We have a table here that shows you the relationships between different delta G values and different K values. And what this table tells you is that a fairly small difference in energy can lead to a very large equilibrium constant and a very large difference in concentration of products versus reactants. All it takes is 1.4 kcals per mole to get 10 times as much of your products as you have of your reactants. Okay, just 3 kilocalories per mole would give you more than 100 times of the product than you would have of the reactant. So small differences in energy lead to big differences in concentrations of reactants versus products. Question? It's closely related to that. So delta H is the temperature. Delta G includes entropy as well as delta H, and we'll address that on Monday. But it's very, very close because the entropy differences are negligible in most organic reactions. And then this last table here, or graphic, just reminds us that if our products are higher in energy than our reactants, we have an unfavorable equilibrium favoring the starting materials and a KEQ less than 1. If our products are lower in energy, more stable than our reactants, delta G naught is negative, KEQ is greater than 1. So understanding the relationships between equilibrium constants and delta G values is important. All right, we'll stop there, and we'll continue with Chapter 6 on Monday. Please enjoy your general conference weekend, and please stay safe and healthy.